Hey everybody, I'm going to try something a little different here. This tutorial is going to focus on the concept of using vectors in game programming. The problems with vectors for a lot of people are that they don't understand a lot of the differences in the way they're used. And my goal here is to try to clear that all up while introducing some concepts that you may or may not be aware of that will help get the results that you're looking for in your game. So I'm going to start by saying that most of the tutorials can gloss over some of the details, at least in the ones that I've seen. So I want to start with the basics, but build up to practical applications for vectors and not just talking about the abstract. And then show you some common techniques that people use, especially the pros in the game development community, that will help make your games more interesting and maybe give you some more power and flexibility. We're going to start off with what vectors are, and then more importantly talk about how and why they're used in games. So first off, vectors are typically 2D or 3D in game programming. If you're doing a 2D game, obviously you're going to use 2D vectors. If you're doing a 3D game, you're going to be using 3D vectors. And since 3D is usually harder for people to understand and to visualize, I figured I'd talk about 3D. And if you want to use 2D, you can employ that pretty easily just by removing one of the components of the vector, and everything else just works out pretty much the same. Okay, let's get started with what is a vector. Now, if you read the definition of vector on Wikipedia, you're probably going to end up more confused than where you started. That's because the mathematical explanation of vector encompasses way more than what game programming entails. You get a lot of theory, you get a lot of abstract, you get a lot of concepts that are not extremely relevant for games, and sorting that all out from what's actually relevant can be pretty hard. So again, I'm just going to focus on what's necessary for games. And this tutorial is going to contain as little math as possible and only really go into it when it's necessary. So obviously, an understanding of math and math concepts is important, but it isn't going to be 100% necessary. It'll make your life a lot easier if you understand the concepts, but it is not 100% required, at least not for this tutorial. And I'll let you know when there's a math-related aspect coming up. So like I said before, vector can be in 2D or 3D space. And in this tutorial, we're going to focus on 3D only. Now, the first thing that can make vectors confusing for a lot of people when they're new to game programming is that there's multiple purposes, multiple applications of a vector. Especially if you're in a game engine like Unity, there's a vector 3 type. And that vector 3 type gets used for a lot more than just what you might think of as traditional vector. It has 3 components, x, y, z, and those x, y, and z are used in several different ways, and I'm going to go into each one of those ways and help clear up one of the main parts of confusion that a lot of people have with vectors. So the first thing that vectors can be used for, the first purpose, is essentially a point in 3D space. It can be represented by a vector. Somewhere out in your world, in the 3D space, there's a point that represents the position of some object, and that position is a vector. A lot of people think of vectors as lines from origin to somewhere else or from A to B. Think of them as points in this case. Then we have vectors that I like to call direction vectors, or directors in a direction. And we'll talk about that one a little bit later. And again, a direction vector is still represented by x, y, z. But it's not a position, it's a direction. And then we have a third type of vector called what I like to call the difference vector, or a delta vector. And that represents the difference between 2 points in 3D space. And you can imagine that as just a line connecting the 2 dots. And that's also a vector. And each of these 3 vectors are very different from one another. Okay. So each of these 3 types are all very useful, very practical, and 100% necessary for pretty much any game you'll ever want to make. So if you don't understand these 3 concepts, you're going to have a really hard time, and that's what causes people to be very frustrated, because things will seem like they're working, and as soon as you try to do something a little bit more complicated, if you're not fully understanding how they work, you're going to get frustrated and it's not going to work, and you're going to give up potentially. Now, I could go into the math of vectors and how adding 2 vectors produces xyz of one plus the xyz of the other, or multiplying vectors or things like that. And that's useful, absolutely 100% very useful. In this tutorial, I'm not going to get into it because I think I can describe most of what you're going to want to do without that. And then that's something that we can cover later, or something you can learn on your own. But I think it kind of takes away from the learning of the vector when you get too much into the abstract. So we're going to focus on the practical, and hopefully you'll have a better understanding of how things work when this is over. Okay, I want to touch on just a couple of basic things at the start here, just to make sure that you're following me the whole way through. First thing I want to talk about is just the idea of units. And in Unity, 1 unit is whatever you decide to make it in real world measurements, or it could be any kind of measurement you'd like. So when something is 1 unit, could be 1 meter, let's say. You can pick any unit you like, just as long as you're consistent. 1 means 1 no matter where it is or what we're talking about. So when we say a vector is 1 unit long, that's the same 1 as 1 unit from the origin. So if I put something at position 1, 1, you'll see it's right at the corner of this square here on the grid. So it's an important thing to note, and just something I wanted to make sure was clear before I continued. Another thing we want to talk about is the axes. And just like in pretty much any 3D editor, you'll see axes shown superimposed on your game world. In Unity, the z-axis represents forward. It's the blue one. It's always blue. And anything blue that you see will be z related. X-axis is red, and it represents left and right, where right is in the forward x. Sorry, right is in the positive x. And just like forward is in the positive z. And then the green axis represents up and down. So y, positive y, means that it's going up above the game world floor, and negative y means it's going down. Now obviously you can always play with these and change them in your game and do whatever you'd like as far as how your gameplay goes, but in general that's how we're doing it. And for this tutorial, that's definitely how we're going to deal with these axes. And then just so it's perfectly clear, if I want to move this enemy here forward, I make a z increase. You can see the z increasing here. I could do it here as well. Increasing z, moving forward and backward when I decrease z. Let's put it back to 0. All right. So this button here represents where you'll see this tool gizmo, is what Unity calls it, where it's placed in relation to the object. It just makes it very clear as to where the actual root of the object is. So pivot is wherever the root of the object is, and center will always be its center no matter what the root of the object is. So if you want to see where an object's root is, you just make sure this says pivot and you'll know. And now if I were to rotate this object around the x-axis, you'll see it pivots from the bottom of the object. Whereas if it were in the middle of the object, it would rotate around its own center, and it may or may not be what you want. All right, so that was really quick definition of the axes in Unity and the positions of the objects. Another thing that's interesting to talk about, and something that maybe doesn't get used enough, or if you're a beginner you may not understand it, is the representation of local and global coordinates for the object. So an object has a direction that is its own forward. So where is its forward pointing? And that's defined by your 3D editor, how the object was created. In Unity, it kind of has a default. So if I were to create an empty, or just create a cube, Unity decided that its forward should be pointing this way, which is kind of the way my objects are as well. And that also happens to correspond to the global forward as well. So the world's forward is pointing that way, and the object is also pointing that way in its own local version of forward. The difference comes in really only when I've rotated the object. So if I rotate this object around the y-axis, now he's pointing in that direction. That's his local forward, pointing this way. But if I change this to global, now he could move globally forward, but still maintain his orientation. Or he could move locally forward and not have to change his orientation forward. So that's the difference between global and local, and that gets used all the time in games. And it's something very, very important to think of. It really comes into play when you're talking about up and down, because globally up is always up, straight up in the y direction. But an object could be upside down, and if it were to move up, does it mean it moves up related to where the object's head is, let's say, or is it up as far as the world goes? And it might be one or the other depending on what you want to do. So that's a really quick explanation of global and local. And this button here just lets you toggle between the two. It makes it easier to see where an object is pointed. And we'll use it later on. That's the only reason I'm discussing it now. Now, another thing to keep in mind is that, like I said before, the root of the object is placed at the position of its transform's position is always relative to the root of the object. So no matter where in the world this object is, it's its root that has that coordinate, those coordinates. The rest of the object just kind of comes along for the ride, so to speak. So in Unity, the transform's position is essentially where the object is, but it's the root of the object. So if you have an enormous object that takes up the entire game world, it's the root that represents where the object is in the world. All right. And then another thing I just wanted to touch on really briefly is I'll be using scripts, and Unity does scripts in several languages. I like to use C#, and I'm not sure how much code everybody understands, but I will go through it as slowly as possible, and I'll try to explain everything as I go. It's these scripts that are helping me demonstrate what's going on and how vectors work. And if you understand them, that's even better. I'll have a tutorial maybe in the future that it goes into actual scripting, but that isn't the goal of this one. So now I just want to briefly introduce some of the concepts I use in my tutorial here, just to make it consistent for you so that you understand as we go forward. I like to use just a couple of standard objects to represent things that are very, very basic, but make it easy to understand some of the concepts. So I'm pretending that this object here is an enemy, let's say, and he's pointing in the direction of this little, I don't know what you call it, looks like a gun turret or something on the front. And it's on the front because notice the Z is pointing that way. Same thing with the enemy, or sorry, with the friend, or not the friend, the player is here, and it's in green. And again, same thing, he's pointing forward. Nothing special there. This yellow blob in the middle is the origin of the game world. It just makes it easy to see where 000 is. And I'm using the grid to represent or to measure the game world in terms of its units. So like I said before, each square is one unit in square. And that helps to kind of identify where things are in the world. So you can see easily if this is 0, 0 right here, this is 1, 2, 3, 4, 5 in the X direction. And that's what you see here. So hopefully that makes it easy. And I'm going to play this little script I've got going here, just so you can so I can talk about some of this. This script is basically having the enemy follow the player around, and I'm going to discuss exactly how this works later on. But just some of the things I use here are, I have lines drawn for where the vectors are. So if I'm going to explain what a vector is or where it is in the world, I use a line to draw for that. And then this yellow star thing is a point. And the middle of this point, this part right here, right there, is the point in 3D space. And these things are just to help identify it and make it easier to spot when it's far away, because you wouldn't be able to see that point so far away if you don't see these little lines coming out. So that helps you kind of see where points are. And I'm going to talk about points and lines with respect to vectors very soon. All right, so now we're going to talk about vectors as position. That's one of the 3 types that I mentioned earlier, and certainly a fundamental concept of vectors, and actually something that people don't even think of normally when they think of vectors. They always think of vectors as like a line with an arrow at the end or something like that, and maybe that's why it's so confusing sometimes. But a lot of times a vector is really just a position. It's a 3D point in space. And the concept of vectors as position and vectors as direction and other things kind of get in each other's way. So let's just focus on vectors here as being just a position. So the position vector of this enemy object is at 5, 0, 0, 5 units from the origin in the x-axis, x direction to the right of the origin. So if we're looking at forward, remember this is forward, to the right, 5 is the position of this enemy object. And similarly, the player object is to the left 5 units. So those are their positions. And again, in Unity, position is, you can access it from script by asking for the transforms position. And I have a simple script that all it does is move the player object to a different position in 3D space. And I'm just going to play it right now. And there he goes. So all I'm doing there is slowly moving the player to the position that I have chosen. And it's totally arbitrary. It's represented by a game object. And I just tell the player to move to the position of that game object. So that game object's position is going to end up the same as the player's position. So, and I just moved it some random place in space. And so that's the position. Here I'm drawing it. And every frame, he's just going to move a little bit more towards that position. So his position is going to become that position. Now, if I were to move the position around, you'll see he'll just follow it. He's not turning because we're not doing anything with rotation, just moving him. So he's just following this thing around. Wherever I put it, he's going to go towards it. So that's position vectors. All right, so to demonstrate direction and how it can be used to affect an object's position, I have attached a script to my player called move forward 1 unit. And this script is about as simple as it gets. All it does is when I click on the object, it's going to add the forward direction vector to the object's position vector. And interesting thing to note here is that this transform.position is a position vector, and this transform.forward is a direction vector. So we're taking a direction vector and we're adding it to a position vector, and the result is a position vector with a new value. And it's really just simple addition, because the forward vector is really just 0, 0, 1 with 1 in the z direction. That just makes the position increment the z value by 1. But I think it's easier to think of it not in terms of x, y, z, but just in terms of what it does to a position. So whenever you add a direction to a position, you move the object however long this vector is in that direction. So we're moving the object exactly 1 unit, because this forward is exactly 1 unit long. In the forward direction, we're going to move the object in that direction. So when I play the script, notice how the root is here, and when I click on the object, it will move 1 unit, which is 1 grid square, forward. And there it goes. And if I keep clicking, it'll just keep moving 1 unit forward. So a variation on moving 1 unit forward would be to move, say, half a unit forward. So I've switched my player to have a script called move forward half unit. And if we take a look at that script, we can compare it to our move forward 1 unit. So here's the 1 unit forward. It's just position plus the unit vector forward. That moves it 1 unit forward. Half unit is position plus forward times 0.5, and multiplying by 0.5 is the same as dividing by 2. And we're scaling by 50%, or however you want to call it. And that moves forward by half of the length of a unit vector, unit forward. So it moves 1/2 forward unit at a time. Let's see that. So here we go. Every time I click, it's moving half a grid square. So very simple, but again, just to illustrate how vectors are scaled and how it makes a difference when you add it to the position of an object. Now in this example, we're going to switch to wireframe view here. I went from shaded to wireframe so that it's easier to see some of the lines I'm going to draw, which will originate within the object, so that they would be hidden by the object itself if I didn't go to wireframe mode. So in wireframe mode, you'll see this better. So I'm going to play this script that I have on my player right now, which is called scale a vector. Basically, it's going to take a vector and scale it by a certain amount, certain number of units. And right now, I've set the scale to 1, so you're going to see a unit vector, a vector 1 unit long. That's this yellow line here. So what I've done is this script that I have, all it does is it draws a line, doesn't do anything else, it just draws a line from the position of the object in the forward direction, scaled by whatever the value I put here is. So a scale of 1 means it draws from the exact center of the object, which is right here, 1 unit forward. And just to make it absolutely clear that it's in the center of the object, well, let's see if I can do a top-down view here. Oh, it's here somewhere. Okay, so there it is, right in the middle of the object. Now if I scale it by 2, you would expect it to go here, right? And that's exactly what it does. If I do it by 4, it goes 4 units forward. If I go less than 1, let's say like somewhere like 0.73, you can see it barely makes it out of the object. It's actually less than a grid square long. And that's simple what it looks like when you scale a vector. Sometimes it's hard to understand what scaling a vector means until you actually see it in action. So that's all we're doing, is we're taking this vector and we're stretching it, or we're shrinking it. So by doing this, we can do all kinds of calculations and tests and things that will make a game behave like a game. And as I rotate my object, you'll see the vector rotates with it. So that's something that's going to be very useful going forward when we talk about rotation, but let's not worry about that right now. Just notice that the vector length doesn't change. It's basically kind of making a circle around the outside of the object. All right, so here's where things start to get a little bit interesting. And these two green stars represent point A and point B. This is one position vector, this is another position vector. The blue line between them is the difference vector between the 2 points. And right now, this point being here and this point being here, you can kind of count 1, 2, 3, they're 4 units apart. These points are. So this blue vector is the difference vector between these 2 points. Now, if I were to move this point around, you'll see it follows, the vector follows the point, and that blue line stays between the 2 points. Okay, that's simple enough. Now, it gets interesting because if these 2 points represented 2 objects in a 3D world, you can do a lot with this vector that's between them. So I'm going to leave this right here, and now I'm going to show you what happens when you take this blue vector and you normalize it. You get a unit vector. Now we have a vector that's in the same direction, but it's only 1 unit long, where previously it was whatever length it was. So let's just go back again. It's whatever length that is. It'll change as I move these 2 points around. So let's just leave them here. That's my unit vector. It's 1 unit long, but it's in the same direction. So as I move this point around, you can see that unit vector points in the same direction as the other point, as point B. But it stays 1 unit long no matter what I do. I can go close, I can go far away, it doesn't matter. It's going to stay 1 unit long. Well, once I have it as a unit vector, I can then make it any length I want, any absolute length I want. So if I want it 1 unit, I've got it 1 unit right now. But let's say I wanted it to be exactly 5 units long. Then what I would need to do is I would need to scale this unit vector by 5 to make it exactly 5 units long. And let's see what I've got it at right now. I have it at length 3. Okay, fine. I'll change that to 5. And now what happens is now I have this yellow line represents a 5 unit long vector in the direction of the 2 points. So now you can see what happens is as I move point B around point A, this vector length stays the same. Exactly 5 units long, and you can see the grid. 1, 2, 3, 4, 5. And now we start to get, oops, sorry, I went under the ground. Now it starts to get very interesting because now I can have a vector that is exactly 5 units long in the direction of between point A and point B. Now if I want it longer than that, this light blue line represents a vector that is a lot longer. I don't remember what it is. It's about, I think it's the square of the distance or something like that. But it's a lot longer. So we can see that if I needed a vector to represent a direction that was exactly this length in the direction of the difference between these 2 points, Now I have that. So that's pretty useful. With this, we can do a whole lot of stuff. We can say when an enemy gets beyond this range, we can start shooting at it. Or we can say that when an enemy gets out of this range, we no longer can see it. Things like that. And let me just bring up a point now that I mentioned it, is something that really doesn't get mentioned very much. And one of the things I was saying before about what the pros do in game development is thinking about vectors and their scale not as necessarily just an absolute number like 5 units long, but when you want to scale a vector, think about how long it might be to begin with. And if you want it to say you want to go half the distance between 2 points, or maybe a quarter of the way there, or think about it in terms of, twice as long or something like that, is think about it in terms of percentages. It just kind of helps, it helps to understand it in a little bit different way. So instead of thinking about dividing something in half, think about multiplying it by 50% or 0.5. A lot of times things go from point A to point B, and at point A it's at 0% of scale, and at point B it's at 100% of scale. So if you want to go halfway between something, that would be 50%, like I said. And if you're thinking about being, say, following behind somebody at maybe a third of the distance to them, you can go multiply by 0.3 or so. It's just another way to think about scaling vectors. So now we're going to talk about vector length. And what does it mean for a vector to have a length? I'm going to show this in 2D because it's kind of hard to visualize in 3D, and it's even hard to demonstrate it in 3D, but you don't have to visualize it so much as just to know what it means for a vector to have length and what it means for your game. So let's start out with the vector that's between these 2 points. This is the origin, and this is some game object, let's say. This yellow line is the difference vector between the 2 points, like I said, and we want to know how long it is. In mathematical terms, the way you would do this in 2D would be simply to make a right triangle out of this line by drawing a line down here and another line over here that would look just like this. And using simple math, the Pythagorean theorem, which everybody should have learned in grade school, that since this is a right angle, the length of this side of the right triangle would be this side squared plus this side squared, the length of these sides squared, added together, and the square root of that value is the length of this side. That's about as much math as I'm going to get into. We don't need to worry about how that works or why that works. That's definitely something important to know, but not necessarily for this tutorial. Anyway, we get a length of this vector just simply by making a right triangle out of the remaining, or out of the 2 points that it goes between. Okay, so now that we know that, we can extrapolate that into 3D just in terms of making it a concept in your mind. You don't have to worry about the visualization part of that. But know that this length is a 3D length. So now we're going to switch gears here and do it in 3D. So here's my player. Here's my enemy. Let's say he's going to shoot me if I get too close. So in order to figure out how far apart these things are, these two guys are, I need to create a vector that's between the two of them by making a difference vector. And then I need to just simply ask for its length to find out if it's within a certain range. I just make up a range that I think is is good for my game world. So if I'm saying this enemy has a range of 10 units, then when it gets within 10 units, it will start shooting at my player. So I'm going to play this again. Here's my player. Right now, they're more than 10 units apart. This big square here represents 10 units. So my enemy is not going to shoot at him, but as soon as I get close enough within range, you can see as I'm getting closer and closer, then he starts to shoot at me. And he's not very accurate because he doesn't turn towards me. He's just shooting straight ahead. But I'm within the 10 unit distance. And you can see that because the line that I draw between them changes from this purple color to the cyan color. And that's how you know that is within range or not. And so obviously this is very useful because it makes the logic for making this gun shoot at the player very simple, just a simple vector length calculation. Now again, just a reminder, note that the root of my player is at the bottom, and the root of my enemy is also at the bottom, so the vector drawn between them is also at the bottom. If you wanted to get more precise and originate the distance check from, say, the turret part of the player or the enemy, you would have to use not the root of the player's position or the enemy position. You'd have to find some root for the turret, and you can do that in Unity. I'm not going to get into that in my tutorial, but that's definitely something that you should learn how to do if you don't know how to do it already. So here, just to demonstrate it from this view, as he gets within range, then the gun starts firing at him. Now I'm going to take a look at the script for this so that it's clear as to what's going on here. So this is a pretty simple script, not much going on. You don't have to worry about the particle system part of it. That's just for fun to show the shooting part. And there's something very, very important here I want to get to. And I will in just a second. But here we're to get the purple vector between the two game objects, this purple vector, it's a simple math operation on the two positions. We take this guy's position, subtract it from this guy's position, and we get, or actually I said that backwards. We're subtracting his position from his position. That gets us this purple line. So when you want to get a line between two objects, you subtract the two. That's all you have to worry about. That gets you this line. When you have this line, then you can get its length. Very simple. I get its length, and when it's within a certain range, then I just start shooting. But hold on a minute. What's this? Why am I multiplying it by itself? And what's this square magnitude here? Okay, so now that's the thing I want to talk about. Now, even with today's modern computers, square root operations are still a bit expensive. And they really haven't gotten any faster, even though processors are faster. If you're doing a lot of these over the course of a frame, you could actually slow your game down. So that's why Unity includes not just the vector length in absolute number, how far away is it, but it also includes the square of the length. That's what this square magnitude is. Why does it do that? Well, because when you're comparing, you don't really need to get the actual length, because you have your range defined, but you can square the range and compare the square of the length with the square of the range, and if those two have the relationship that you're looking for, so if the square is less than the square of the range, then you know you're done. You know your calculation is correct. The player is within that range. And the reason why we're doing this is because comparing, if we were to take the actual magnitude, we'd have to take a square root. And like I said, those can be expensive if we're doing a ton of them every frame. So there's no need to take a square root, because we can just compare the squares together. And that actually will be a little bit faster. And again, it really depends on the hardware it's running on, but in general, it's something that's one of those pro tips that I was talking about before. This is done very much very commonly in the games industry. So comparing the squares is definitely better. You can make this a constant. You don't have to call it, you don't have to say gun range times gun range. You could just make it a constant somewhere else in the script and do it, calculate it there, and then just call it by its whatever value, gun range squared or something like that. And if you want, you can even make this into a function if vectors are close or something, like, or vector within range, just to make it easier. But just a little tip there when we get into vector comparisons of vector lengths. All right, we're finally starting to get into some of the fun stuff. And we're getting a little bit more practical with what a game might do. And a lot of the examples that I've seen that try to teach this, you just see one game object move to the exact same spot as another game object. And that's okay, and I think I already demonstrated something very similar to that. But I'd like to show you something a little more practical and that uses the concepts that we've just learned. So I'm just going to play this, and I'm going to explain what's going on. So here's my player, and he's got a script that's on him that basically says just move to a random spot every few seconds. So that's pretty simple. He just moves to a random place in the game every few seconds, and the enemy is running a follow script that's going to stay within a certain distance behind the player. And that's where we start getting into how to do that operation, how to do that logic. If you didn't understand the concepts that I just taught you, this would be kind of hard, actually, to do. You might get really confused as to how to do it or how to do it properly. So let me explain what's going on in the script, and hopefully it'll be pretty clear and pretty obvious at this point as to why this works and how it works. So while that's playing, I guess I'll bring up one of the scripts that I'm using. So this is the follow behind script. And in order to do this properly, first let me pause it. First we have to take the player and we get his position. And how do we go behind the player by a certain distance? One thing I didn't mention, and let's just show that off here, is this follow distance is set up by the script. So this can be as long or as short as we want it behind the player. It can even be like in front of the player if we do it negative, but we don't want that right now. So you can see how it's changing as I change this distance. And that enemy is actually quite confused right now. He's trying to go to that yellow dot. So let's just leave it somewhere like that to make it far away. Okay, so I'm going to pause it. Let's take a look at the script. So follow behind. We need to get the target position is on the enemy is just the player. So the enemy chose the player as his target. Okay. So the enemy is the target. His position, we're going to get a vector that is the target's position. So we're taking a position vector, which is here, and we're going to subtract it from the target's forward position multiplied by the follow distance. So that's actually like 2 or 3 operations all in one. And if you remember what I had demonstrated a little while ago, this is using just that. So you might have to kind of think about this just a little bit in terms of what I explained before and how this works. But if we take a position and we subtract, if we add a vector, remember we added the forward vector to the position and went a some distance in front of the player. By subtracting, it goes behind the player. And when we scale it by a certain amount, we are essentially setting that length. So when I change this to 1, and let's just go 1 frame, that's a unit vector now. That's just 1 unit behind the player. So that's essentially the same as me just getting rid of this multiply, because when you multiply something by 1, it doesn't do anything, right? Position minus forward would be position minus 1 unit worth of the forward vector is 1 unit long, so it's taking the center of the player and moving it back by 1 unit. When we scale it by the distance, then it gives us that long vector. So hopefully that makes sense, and all that stuff that I explained before should hopefully explain that. If not, you might want to go back and watch it again. So there's 8 units behind the player. And then we go back here, and the rest of this is not part of the tutorial, but it is just something to make it look a little nicer. We'll talk about rotations and quaternions and what slurp is and all that other stuff later on. Even this lerp here, don't worry about that. The important part is figuring out what this vector was and how to get this point right here. That point is behind, and behind is a position vector created by taking another position vector and subtracting it from a direction vector, just like I explained before. Okay, so now this is where the real fun begins. We're going to see how understanding the way vectors works allows you to do some really cool stuff, and you'll probably look at this and say, oh wow, I can think of 100 different things I could do to make that better, and that's exactly what I'm looking for. Because this is about as basic as it gets, but there's a lot more complexity you can add to this. And as long as you understand these concepts, you can really do a whole lot. So let me explain what I'm talking about here. So what I've got in this scene is 6 boxes that are actually physics objects in Unity, rigid bodies. Hopefully you're familiar with those. If not, you should probably learn about those on your own. I'm not really going to get into that here, but when you add the rigid body component, then these objects will behave like real physical objects. So that's what I have set up here. These objects are resting on the ground, and this example actually does take place in 3D. I know I've done a lot of 2D so far, even though I said I was doing mostly 3D, but this is going to actually use 3D for real. And so what I've done is I've created a script that's basically an explosion source. So something like a bomb or missile or whatever, something that would explode and force anything that's near it to be pushed out in the opposite direction of wherever that explosion source was. So you can it's under the ground, so you can't see it through the floor, but it's there. And I guess if I turn on wireframe, maybe it's easier to see it. So it's there under the ground. I'm gonna leave it shaded just to make this look better. It'll simulate a little bit better if I have it shaded. So it's under the ground, and when I play this, I'll play it once and I'll explain what happens after. Explosion source under the ground, it ticks down 5 seconds, and then it pushes anything that's within a range out away from it with a force of some type. And the parameters to the script that I have are the radius at which the bomb, let's say, will affect. So I have about an 8-unit radius, and again, this large square is 10 units square. These little ones again are 1 unit square. So you can see that 8 is about right, because that's more or less this sphere. A radius 8 would be out here somewhere. So that's fine to get all these objects. And okay, so and then there's a scale that I'm adding to the force, and I'll explain what that is when we look at the script. So let's take a look at the script. I'm gonna put it over here, and I know I've done some additional things here that are more related to Unity and less related to vectors, but it's just the way I'm used to writing my scripts. So don't worry about stuff that is kind of maybe is a little foreign to you. The important stuff to know is I'm getting a list of objects that are within a sphere of my explosion object. This script is on the explosion source, which is my my sphere down there below the floor. So anything that's within the radius, which again I have as 8 of me, goes into this list, and it's a collider. That's the object that results from this overlap sphere test. So for each of those colliders, what I'm going to do, here's where we get into the vector part. So I take the collider's position, which is the position of, say, one of these boxes, and I subtract my position, which is the explosion source. And if you watch the earlier part of this, you'll know that that gives you a vector, a difference vector. That's why I call it diff. And that is basically a line drawn from this vector to, this position, to the explosion source's position. And that's represented by these purple lines at the beginning of the script. And they go through the floor, so they're kind of dimmed out. But you can see they're connected from this object straight through the floor to the bomb. All right, here I've modified my example to spread the cubes out a little bit more in more of a random pattern. And what I'm going to show here is how we can take their proximity to the explosion source here and use that as a way to figure out exactly how much force there should be when the explosion occurs, and how much force should occur to push these blocks away from the source. So I've modified my script a little bit, and let me bring that over here. So if we look at this, it's pretty much the same framework, but the important thing to note is what I've done here with the vector calculation. So I'm going to run this, and again, there's your purple vectors pointing at the source of the explosion. Now let's freeze it right here. Now take a look at what happened here. I've got different vectors going away from the source, the explosion source, but they're different lengths, you can see. This one here is a lot longer than, say, this one right here. And that's because, actually, let's see. Yeah, they're different lengths. And that's because these blocks started off in this position. So some of them are closer to the explosion source than others. So this block here would get more of a force away from the explosion, where this one would get affected less. And as I play it, I'm going to pause it again just about when the explosion occurs. And you can see that this guy here, he's not going to go as far as maybe this one here will. So you can see that guy got pushed quite a bit out, a bit away from the explosion source. So how did that happen? Well, it's the same enumeration through the cubes, and it's the same difference calculation that gets us that purple vector. But here what I'm doing is I'm saving off the distance away from the source in this distance variable. And here what I'm doing is I'm normalizing the difference vector between the explosion source and the cube. And by doing that, it allows me to get it back down to a unit vector, which would then allow me to scale it back up to some arbitrary value. If I didn't do this, I would end up with this vector unnormalized, and it would be whatever length this is, it would stay that length. And I don't want it to be that length. I want it to be a specific length. And I can't make it a specific length until I get it to be unit vector. Once I have it as a unit vector, then I can make it a specific length. If I tried to do it without normalizing it, I wouldn't know the calculation for this, or at least it wouldn't be so easy to figure it out. I'm sure there's a way to do it, but this is the way that I do it, and this is much easier to conceptualize. So once you get it into a unit length, then you can make it any size you want just by multiplying it out. In my case here, I'm going to do something a little more complex. This is a little bit of additional math, but hopefully it's not too terribly hard to understand. So we're going to create a force vector, and a force vector is a direction vector where the magnitude or the length of the vector determines how much force there is. So in the three types of vectors I talked about before, the position, the direction, and the delta, this would be number 2, the direction vector. And the magnitude of this direction vector is how much force there is. So to make that vector, I'm going to take the normalized vector in the direction of the way the object should travel. So if I didn't add any of this other stuff, it would just go 1 unit of force away from the explosion. That's okay, but that's really not that exciting. So what I'm going to do is I need to scale it by something. So instead of being 1 unit long, it's going to be longer than that. I want it to be longer than 1 unit, or potentially shorter, but in most cases it's going to end up being longer. But I want it to be attenuated, and that's a word that's kind of used in multiple disciplines, but I want it to be limited, I guess is another way to put it, or actually, make it longer or shorter depending on how far away the object was from the explosion. So by doing this reciprocal 1 over the distance, it allows me to kind of invert the relationship between how far away the object is and how far it should move. So the further away it is, the less force there should be. If I didn't do this, if I just did it just with distance, then the closer it was, the less force than there would be. And that doesn't make sense. Things that are closer to an explosion are affected way more than something that's far away from the explosion. So to invert that, I do 1 over the distance. And that does the inversion, but what happens is it makes it kind of a small number. So to get it back up to something with enough force to actually move the object at all, we need this scalar. So like I explained before, we want to scale the vector. We multiply it by some number, and that would lengthen or shorten it. So we get the 1 over distance, which gives us that inverse relationship, and then we scale it back up by a certain number. And I think I use something kind of large, like 40. So that gives us the effect we want. And then the other thing that I did, so that's our force vector. It's a direction vector with a magnitude that is exactly what we want it to be. And if you're familiar with Unity, then force mode impulse means do it all at once instead of applying it over multiple frames. So we want all this to happen at once. Just push the thing. Don't slowly move it. And then this line here is completely optional, but it gives it more of a realistic effect by adding some random torque to the object too that makes it spin a little bit. And so that looks like, let's just run it again and we'll see what it looks like. You can see the closer objects get pushed further out. They do this nice spin in midair. And and then we get the effect we like. So we're just about done talking about the ways that you can use vectors to affect your gameplay, and maybe you learn some tips and tricks along the way. I just want to add another little tip or point that comes up quite a bit, and another one of those things that the pros tend to do, although it's probably pretty obvious anyway. But just in case it's not obvious, there's something that tends to come up a lot where especially when you're dealing with rotation of objects or having something point at something. In this example, I'll just play it and I'll explain it as it goes. We have an enemy object. Think of it maybe like a tower defense game. This is just a tower that's just pumping out bullets, and this wouldn't really be how you do it, but just the way to illustrate it. This guy is actually aiming at a target on the ground. He's aiming at this guy, but he's not aiming in the air because maybe he's only able to shoot at the ground. And maybe the idea is that he's shooting some sort of explosive that explodes over here and has an area of effect that goes up here. Something like that. I just made up an example that I thought might help illustrate this. But what this is doing is it's eliminating the y coordinate from the vector. It's treating essentially a 3D vector as 2D. And this happens all the time when you don't want to deal with anything, say, in the air. You just want to deal with stuff on the ground. And so as I move this guy around, my enemy tower is gonna point at it, and he's gonna shoot in that direction, but he's gonna shoot at the ground. He's gonna be shooting underneath the whatever this thing is. So no matter where he goes, up or down, nothing changes. And that's because we're not looking at the y coordinate. Again, this may be obvious, but just in case it wasn't. So the way this is accomplished is basically this fire routine just keeps shooting over and over again, depending on the rate of fire, which is not really relevant to the example, but just thought I'd explain it anyway. So what we're doing here is we're taking the target's position, which is the sphere, and recreating its position without the y component. There's different ways to do it. I kind of did it this way. You could copy it and zero out the y, whatever you like to do. I think this just makes it clearer what's happening. So I'm taking the position and just putting a 0 where the y was. So that eliminates the y from the calculations. Then I'm going to take the difference of the two vectors, and that's going to give me a line from the xz, which is just the ground coordinate of this enemy, to the ground coordinate of the whatever that target is. And just think of it like a projection, like if you were to shine a light straight down, it's where the shadow would be. And so that way, any length calculations or any rotations will deal with only ground-to-ground coordinates. Don't worry about the rotation. We'll talk about quaternions another time. But basically, what I'm doing is I'm just eliminating the y coordinates from the calculation here for the difference.